Okay, so welcome everybody. Today I was invited by Dinah to present a little workshop on the signal quality measures of fNIRS, and it will be separated into two parts. The first will be just a general presentation, giving you some insights on which factors can influence the signal quality in fNIRS. And then we will look into different data sets and try to really by hands-on evaluate how much these different signal contributions are influencing our signal. So I'm using a lot of slides from Franziska Klein because she makes really nice images, and yeah, that really nicely shows what is part of the signal. And so here the whole process of the signal quality starts already with the probe design. So basically, which region of interest do you want to measure? Because signal quality can only be as good as the region that you really cover with your fNIRS signals. So after the part that you have decided for a specific location, you have to place the cap as good as possible to really reach this location that you have determined. So it's not only that you know which region you're planning to measure, it's also the second step that you are really sure that you're using the right location there. This can be done to ensure that you have the right location, can be done by spatial validation using, for example, an MRI reference scan and then performing neural navigation. Or you're using, for example, high density setups, which cover a broader region or can cover a broader region, but with this also increasing the potential that you hit the right spot. So this gives you a much bigger chance to really measure from the right signals. Today we'll mainly cover the regular distance of fNIRS. And there, yeah, you can see that there's also the challenge. You only have a limited number of channels, so you need to decide where to place your optodes, and then you also need to decide where you will have potential blind spots, so where the fNIRS signal is not touching the gray matter. So if you have done all these pre-preparation steps before you even start measuring any signal, you then basically set up the cap and you are trying to like minimize the error of bad data quality, meaning, for example, the scalp coupling. So how good is the optode attached to the head? And you want to have this not only for the beginning of the session, but you also want to have this throughout the whole recording. So imagine you're scanning or you're measuring for half an hour or 45 minutes, and you have just different experiments throughout the session where you didn't randomize, for example, the order of the different sessions. And if there's, for example, a session that is more in the later part of the experiment and your optode placement is not optimal, then it could be that your findings are not really based on a worse response to the task, but just because your optodes are not like fixed anymore, and over time you got a worse signal quality. So it's also important to check the data quality over time and see if across your sessions, across your runs, that you still have the same assumption, the same data quality, that you don't draw wrong conclusions just based on the signal quality that might have changed. If there are artifacts in the data, there are processes that you can correct them. So just looking at the data quality and saying, okay, I just rejected the bad channel is also not required. You can also try to correct your data, and after the correction, decide again if you want to really keep this data set or if you want to reject certain channels or even certain data. So specifically for fNIRS, we're usually talking about motion artifacts that are arising, because one of the great advantages of fNIRS is that you can have real-world scenarios, so real-world setups. And these are really the parts where artifacts could occur. For example, also movement tasks, but here just walking the dog and recording fNIRS could be something where you want to correct for these artifacts that are just possibly more happening than in just an environment of the lab, for example. Then next to the normal signal that you're getting, you want to do the processing of the signal that is not an artifact. It's really like physiologically measured by fNIRS, but it is maybe covering the signal of interest, namely the hemodynamic response from the brain that you want to measure. So there are definitely different techniques that you can use, but we just cover this as a temporal filtering, for example, where you can remove, for example, the heartbeat component from the signal, which in the first part we used to figure out if we have a good signal or not, right? So it's important that across these different procedures, we are making use of the signal, but then also removing it later on. So they are really working together quite nicely, but it's important to also know, okay, when to apply these specific corrections. So the data quality assessment is much better if we have already, like if we haven't even processed our data, because then we know, okay, what is our starting point, and then the filtering afterwards can give us the details. Okay, does it make sense, the data that I'm looking at right now? And the temporal filtering shows you very nicely how the unfiltered and the filtered data changes. For the extracerebral activity, it's a bit of a bigger challenge. So there, it really includes signal that is in a very similar time domain as compared to our task frequency, maybe, and it's much harder to disentangle that. So if you are lucky and if you have a current fNIRS device, you usually can make use of short channels that are basically too close together that they don't cover the gray matter or the signal of interest, but they reach the extracerebral components. So they can be used to regress out these signals that are highly overlapping with the signal of interest that you're looking at. So this is also part of the signal quality, because we are looking at a specific signal within our NfC signal, and that is the functional activity. And therefore, we have also to consider in the signal quality, even if the signal looks perfect just by the general channel quality assessment, it could be that the signal quality of our hemodynamics does not yet look good enough. It doesn't follow our expected response functions that we are assuming, and also from the averaging we wouldn't get a good signal. So it's really important to look at signal qualities in different levels across your pre-processing pipeline. So looking a bit more into how a good and a bad channel looks like, this is something that you will experience very quickly when you dive into fNIRS. So the interesting factor is, of course, the heartbeat that you usually see in good channels right away. But in more noisy signals, it's of course very challenging. And dependent on the measure that you're using for this signal quality assessment, which I will come to later, you will get like different scores on the data quality, which can help you immediately assess how your data quality for a specific channel is, but also how this data quality is located on your specific montage. Because it doesn't need to be that only one channel is bad. It could also be that the relation is to a certain region in the brain or on your setup. In that case, if you experience this more often, that you see on certain channels a higher chance that there is a bad signal, you should reconsider some of your cable management or just the placement of the optodes. It could be that they are too close, too far in a way that they form a bulky sense that maybe have some weight and is pulling down on the cap. There could be many reasons, but this is very important. If you see a systematic effect of bad channels across participants, there is a high chance that you can correct for that just by optimizing the setup. Looking at the frequency spectrum of these two components, you can see that they are like rather similar in certain frequencies. Yeah, so you can see that the amplitude is much bigger for the heartbeat component, but there's still something in the signal. So you would be able to just say, okay, this signal looks bad, I just reject it completely. But you could also go one step further and say, okay, I try to correct the data, even though I see there's no direct heartbeat signal in there, which I can set as a requirement. That's totally fine. But you can also go one step further and see, okay, if I filter the data and then look at the channels, and if you still see that the channels which are maybe close by are having a high correlation after you've done the processing, it means that this channel was still covering good information within the signal. So it is part of the whole pipeline to see if that matches. And looking at the frequency spectrum could be one potential way, but we will do this in the hands-on in a bit more detail. So there are different methods, and I think many more, but these ones are, I think, the most commonly used methods to assess the data quality from the general signal. So the coefficient of variation is, yeah, I think was one of the most often used together with the scalp coupling index, and these measures are using, yeah, basically trying to figure out if the variability in the signal is, for the CV, for example, is not exceeding a certain threshold, whereas the scalp coupling index is basically measuring the two components separately, so the two wavelengths, and figuring out if we have a coupling of the hemodynamic signals within their frequency. So they are doing a cross correlation to assess the signal, and we can look at it in the data later on to see how these different types of measures will give you different results and different thresholds of rejecting or including channels. And there is also the signal quality index, which gives you basically a rating from 1 to 5, indicating a very low and a very high signal quality, which is run into different stages where the data of the quality is assessed. For today, we will stick to the CV and SCI, and we will just look at the data, how it's basically spread. Now, we were talking about motion artifacts and also some physiological artifacts. One important aspect that you have to consider is that these effects or these artifacts are not just independently happening, they could even happen at the same time and in the same data set. And even while a motion artifact is happening, there could be also microwave in that moment. So these even though we do these steps one by one for the correction and the assessment, these events are happening sometimes even overlapping at the same time. So it is important to also consider that these events, when I'm looking at the raw data, which could result in a bad CV, that this, after running certain corrections, could be a bit leading to a better signal. But one of the important aspects of the motion artifacts is related also to these jumps in the signal that you can see. So the baseline is shifted into a different moment, and this can happen just within one run once, but it can happen multiple times, and it can induce different shifts. Most of these shifts and these artifacts can be nowadays corrected nicely with wavelength correction methods, or TDR, or CBSI, but always in combination with the filtering of the signal that removes also the slow trends after the processing, because this would still have a slow trend in the data. So the filtering is also here an important aspect, also a requirement for certain statistical measures that you're using. These slides and also some of the following slides are provided from Dr. Amaya Benitez. So she prepared a few of them as part of the lecture series in Maastricht. So just wanted to present you some images of the motion artifacts. So how does it look like in specific time windows if I have a motion artifact, if I have corrected it with different methods? And that's also one of the aspects. When you publish an article, you decided for certain pre-processing. And it's therefore very important that it's clear what you have used, and also argue why a certain method was more in favor of your decision than another one. Because that is, at the end of the day, when we do meta-analysis, this argumentation why you choose a certain method is very important to understand also the rationale why we have a certain distribution. It could even be that certain, or that's also what you have seen, that certain artifact correction methods work better on, for example, movement data compared to resting state data. And that's really important to consider. And then there are, like, for example, for the CBSI, there are a few requirements for the signal that you can apply these motion artifact removal. So here you can see that after CBSI, you get a 100% anticorrelated signal, because that's part of the processing, that it combines oxy and deoxyhemoglobin into a full anticorrelated signal. But you need to be aware that this is only possible if in the beginning, the signal was already in a way anti-correlated, so that the motion artifact correction could also work, because then it would be able to find differences that were induced only by the motion. But if your signal just from the beginning was not anti-correlated, this method has a bit of a hard time to disentangling these artifacts. For the TDDR, one of the advantages is that it's fully automatized, so you don't have to set any parameters, and that helps on the standardization quite a lot, because you can just run this method and don't have to worry about specific artifacts. You can combine these methods with any pre-steps, for example, removing of spikes or certain preprocessing, but they have all their own requirements. So if you apply after the assessing the signal quality and you decide for a certain method, important that you keep this method throughout all participants, because otherwise you can't draw any conclusions on your sample. But within this decision, why you choose one over the other, you can best look at review articles telling you the pros and cons of each method, and then decide for one or the other. Then I think you know this very famous slide telling you more about where the fNIRS signal is coming from and what it basically includes. So the assumption and reality, as you can see, is very different. And I think this was one of the slides that forced everyone to use short channels in the long run, even though there are now also nice opportunities that you can use just the general signal from your fNIRS, but short channels is a nice independent measure that helps you a lot to regress this additional non-evoked responses, systemic activity, and gives you just an independent measure, which is spatially related to your fNIRS signal, which is very important. So the short channels are different across manufacturers, but basically the most important aspect is that the distance of the short channel compared to the normal channel is about 0.8 to 1 centimeters. So it's much shorter, and that should cause that the banana shape is not reaching the gray matter. And there it's of course always a bit of a question. If you are measuring infants or younger people, it could be that the head size and the distance is already too big, that you already reach with your short channels the brain. So you have to really take care that this is not removing the signal of interest from your data. But with the short channels, you really have the nice addition of an independent measure. Now you would usually ask yourself, how many short channels do I need? And there is a variety of articles telling basically that you can use just a few short channels, that you can use one short channel, but that you can also use a huge amount of short channels that you can then use, for example, to run a principal component analysis to get more a centralized measure of the extracerebral component. So in that case, for your specific design, it would be good that you run a few pilots to really figure out, okay, what is for my sample and for my specific setup and montage the best combination of short channels and normal channels. So that is just a general advice. You can, of course, look at the articles, but then if you don't replicate exactly the setup and the montage that they have used, you have to adapt to your specific montage and try to just establish that this amount of short channels is enough for the specific task. And there it's also important, as I said, the short channel is location dependent. Also there, if you have a short channel on a certain place, but only, for example, one, it could be that this short channel is highly sensitive to only the normal channels that are close by, but for other channels, it doesn't help as much. So there you have to consider a bit where you are measuring and how homogeneous your cap setup is in that sense. So coming back to the very first start, when we are looking at the cap setup, we really have to make sure that the optode can touch the brain or the skin, not the brain. And there are different methods how you can do that. But most importantly, there must be a nice check that this is valid throughout the run. And usually you don't have time to individually check each of the channels if you have, for example, a huge montage. So you really have to also get a hold of the amount of time that you need to prepare the cap and the general quality that you want to achieve for this specific task. And that is really a procedure that is extremely different across your tasks and your designs. So I will show you different montages where you can see that just by the pure amount of optodes, you just will see if I need 1 minute per channel or per source or detector, it will just explode, and you can't even do that if you would individually try to optimize. So there, you have to have some measures. One possible advice here is that you also get a questionnaire for each of the participants that gives you some indicator of how good this participant might be for this study. So that is Dr. Bettina Sorger published a nice article about that, where you can get some independent measures of hair density, hair color, skin color, like all these things that influence the fNIRS signal, which then can give you the additional information for your post-hoc analysis, why there are certain differences in the group, for example. So if you have these measures, by just writing it down, just filling out a questionnaire, this might help you at the end to figure out certain differences across your group, or even within the group. Then the caps must fit properly. So even if you set the channel correctly, if the channel distance is different across the participants, you have to make sure that this difference is as small as possible. So using the right cap size for the individual participant is very important. And yeah, this really differs quite a lot. So here in Maastricht, we are quite happy that we have a quite homogeneous sample of female students, psychology students mainly. So we usually can scan with 56, 58 sizes, but this of course also matters a lot within your sample. And you have to take care that this is not influencing your results too much. So you should really take care that this cap size fits to your sample and that you adapt accordingly. So the fNIRS probe must also cover your region of interest, which I said in the beginning. So the anatomical reference is very helpful. You don't have this information with fNIRS directly, but what you can do with fNIRS is using, for example, a localizer or a short run where you can determine if the setup itself also includes the response from the region of interest that you're looking at. So there are certain, just for certain tasks, you can basically just have a short run of about 5 minutes where you can get an idea if the activity that you want to elicit is also present in your current data set, which could help you before running a whole session of an hour, for example, to determine if the cap and everything is set up appropriately, and then you can continue with your scanning if you don't have an anatomical reference and can't do neuronavigation, for example. But even then, you should, of course, try to put the cap in the EEG positions so that you are there as close as possible. Always map the right location and try to minimize. And there are some nice EEG articles about the influence of this good positioning. And so if you don't have any external measures, really try to place the cap as good as possible based on the 1020 system. The neuronavigation is really the one that helps you also post hoc to verify that the locations that you're measuring and that you're looking at are really the points on the head locating to the best possible location for this individual. And there's also the other fact for the high density setups that are more and more coming. There, since you can place them very flexibly, you can also adjust them individually for each participant and place them as good as possible to optimize the coverage and the signal quality there. So this is this is another opportunity to compare across your sample where you have placed your optodes. But it's also something which most of the people maybe not have, and it takes also some time to do. So current developments show that you can also do video recording of the participant and then post hoc basically reconstruct the position of the cap on the head. And since we know that these things are coming, it's a good advice to do these recordings, even though you might not directly use them. So just check out what are the requirements for these AI-based methods where you can do post hoc opto placement. Just do these recordings, and then you can decide if you still use them or not. Or but at least you have the data, and you can post hoc then still decide what to do with the data. So if the optode locations are clear, you still have to have the reference of the specific location. So this is more to the idea, how do I find my best optode placement? Because this also is the main part of the signal quality. If I measure the best signal that I can have from the aspect of data, meaning just the raw fNIRS data, it doesn't mean that I covered the right region, which is interesting for my task and for my general experiment. So therefore, signal quality goes here into the very important aspect that you need to cover the right region. And this is different compared to MRI or fMRI, where we usually have enough voxels and a slice that is big enough that we cover the right regions. And even if we don't have this as a focus, we can look at the whole brain and just figure out later on. Here, if you see that the activity is at the edge of some channels that you are covering, but then it's like basically reaching out that you can't recover that. It's just you haven't measured this signal. So it's really important that you verify your placement with some pilot data, if possible, to just really have a good idea that the decision that you've made, because you have to decide at some point which channels to use, that this is on a good fundamental basis. Yeah, and then the interopto distance, which I said already with the sizes of the individual participants, it's also that the sizes do differ even within a participant, just because of your general placement and decision where you have the optodes. If you're using the 1020 or 10.5 or like whichever system from the EEG, you can also there decide how you place and at which range you basically put the channels together. So looking at these 3 centimeter optimum, you will figure out very quickly that it's not 3 centimeters all the time, and that it can differ from 2.8, 2.5 to 4, 4.5. And you still get, for good fNIRS devices, you still get a good signal with these ranges, but you have to consider that this is a difference across the channel. So you can't assume that all the channels are measured with the exact same distance and the exact same channel quality. So this is really also an important aspect, that if you design your channels and you're really at the limit of the distance, so that you see, okay, I'm getting in 5 out of 10 participants problems with my signal quality just because I'm reaching this 4 centimeter mark or 3.5, then you should consider to make it better, a bit smaller, like the 3 centimeter optimum, to really get in 9 out of 10 or 8 out of 10 participants a good signal. Because at the end of the day, if this channel, which is the meaningful channel for your experiment, is not covered in most of your participants, you just have a much smaller sample. That's just how it is. And this smaller sample you can easily avoid by just checking that you're not reaching this limit. So this is from the factor of your design choice of your optodes, and to the right decision then what it will basically include. So I think I've talked enough about potential and how it could look like. So we will now look into some data, and we will use 2 different applications. So one is the Satori educational version, which you can just download and also try everything that I'm doing right now yourself later on, to just get a hands-on experience how the data can look like, and which basically procedure and steps you can follow. So I open, for the first part, I will open our Getting Started Guide material that is including some bigger coverage, and we will just jump into the data right away. So I don't go into details of the software for today. So just try to figure that out when you download the software and want to play around with it yourself. But just look at the general signals and the channels to really get an idea how the quality does look like. Now, first of all, you can see that this specific pattern that we are looking at is a bilateral design, and we have split basically between left and right hemispheres. And in this design, we also have short channels for a lot of normal channels. It's not completely covered, but we have a lot of these short channels around. So the first thing that we were talking about was the heartbeat, right? So when looking at the individual signal, you can nicely see in this data set, for example, that we have a visual heartbeat that is from the beginning to the end with the same amplitude. So it's consistent. And it also shows this across different channels. This you can just see by eyeballing within the event-related averages here. So that is really, really straightforward to look at. But you can also see that by looking at the spectrogram, which I was telling you before, which includes here at the heartbeat frequency. You can see that you have here a clear pattern for these specific channels. So that is first of all also a good sign that we have this specific range here in our data. And you can see that there are no real other artifacts right now that are directly visible. So meaning, for example, motion artifacts. So this was a lab environment. Participant was sitting still, so we don't have huge artifacts that we are currently encountering. Still, we can use this data to just apply, for example, our really objective measures. So I will just run in the pre-processing just the channel rejection, and I will start with the SCI, so the scalp coupling index, and I use the default value here that we have of 0.75. So everything below that value will be rejected. Everything above will be seen as good because this is a correlation value. So a high correlation between oxy and deoxy, or in this case, our particle density values, will be seen as a good signal. So I press just go. And what you can see now is that nothing changed. And that is a good thing because it basically means that no channel was rejected. Yeah, and we get really high values across the board. Yeah, which is pretty nice. And we can also now check if this is coherent for the map. So I just go overlay channel maps and look at the distribution of this. So I can just load the results of this map. And then I can see that on all of the channels, I get a pretty clear response. So these values are all 0.8 to 1, so really high, which is great. So let's use a different measure. So for example, using the coefficient of variation. And I just overlay that result here. So this is the CV map. So this is a bit of a different measure. I have to adjust the scaling so that you can see it better. So this is from 10. Yeah. So here you can now also see that this also these values, so it should not exceed the 10, also are very clear. But we can now see that there is also a pattern within our data set. So it's a bit of a different measure. All of them, so both of them would tell you that that the signal is, that no channel is rejected. Still, they are sensitive to certain aspects in the data. And that's an important, an important measure. And the same would be for the other measure, which we don't touch today, that they are really giving you a bit more trends inside there. So let's look at another data set. So we look at the second run for this participant. And you can again just see the same idea. So you look at the channel heartbeats, yeah, and you can also look at them in the deoxy signal. And here what you will always see is that this heartbeat signal is not as clear as for the oxyhemoglobin. So if I look at them at the same time, you can see that there's a huge difference, but this is to be expected. What is important is that what I told you about the requirement for the CBSI motion correction, that these two channels are anticorrelated, we can measure that as well. So I just go to analysis and go to anticorrelation, which will just perform the correlation of oxy and deoxy signal. And then you can see that we are expecting negative values. So just on the raw signal, negative values across the board. And you can see that for some channels, even though the signal looks pretty nice, you can also see that they are not as highly anticorrelated as they should be. Yeah. But this is now looking at really the raw signal without having done any pre-processing. So this is also a nice indication measure. If you have negative, like an anticorrelated map, that's a pretty good starting point to look at. So let's do some pre-processing and look at the change of this map. So we just apply the standard pre-processing. So all the standards across the board. And then we can look again at the anticorrelation. And now we can see how this correlation is basically changed based on the specific channels. And you can also see by eyeballing that this is now having a clear pattern. Interestingly, this pattern that you see looks pretty much similar to the signal to the map that you knew from the CV before, where you can see here this pattern compared to this pattern. It pretty nicely overlaps. So the information in the signals are quite quite clear, and they are very consistent. Now we could think of different reasons why this specific step was happening, but this is for every data set is exactly the main take home. So you should evaluate for your data set which parameters are the best with respect to your design and what you want to choose, and you should write this down and argue in your article why you choose for this specific method, because that will help us on the long run to determine the right and best method for specific tasks and for specific designs. Having one task, like one pre-processing pipeline for everything would be, of course, amazing, because then we can compare everything, but that's usually a bit far-fetched, so it will take some more time to look into these aspects. So one of the things that we can do in addition to just looking at individual channels is to look at the whole time course of the events. And here you can see the time course just color-coded, that you can also see the influence of specific moments in the time course and the amplitude changes in certain channels. So what I told you before is that that this cap is organized in left and right, and also the channels are organized on left and right. So we have a certain cutoff for a channel number, which then goes into the other hemisphere, which you can see here. Yeah. So this is then going to so with S9 we are on the other hemisphere, and you can clearly see the two patterns evolving. And this is one important aspect, that you can also try to organize on your cap design to place the optodes so that they are close in location, but also close in numbering, which makes your life much easier when you do this multiple plotting. So here, for example, you can see nicely that they induce the same response for the same sources and detectors and channels, which makes it much easier for you to determine, is this artifact spatially consistent, or is it just one channel that is affected by this specific artifact? And you can look at this data, of course, also on the while it's completely unpreprocessed. Yeah, so they can even see if certain channels are having a higher or lower heartbeat. So here you can see that some of the channels having just not as nice signal to noise than others. But this gives you a nice way of of examining your data. Can you do this for each and every participant? No, because that is really a lot of work, and for a lot of data sets a problem. So you should really decide at a certain point in time which preprocessing is the best, and then apply this preprocessing standard to all your data sets. There can be certain moments where you can, for example, have additional measures that point out certain amount of artifacts for certain participants, which you can then look individually to see, okay, can I still recover that signal? But this is also something where you have to be careful and argue very clearly why did you perform this step different compared to the other participants, and why you think that this is not a problem within the analysis later on. Okay, so I'm just opening one more data set here, which is a bit of a unique data set because it covers a region twice. So this is the exercise 1. Oh, I didn't even have download, so I just downloaded the data, and it should be now available here. Yes, X1. So this data set is giving you, like, first of all, this channel layout. But when you look at the channels in depth, you can see that these channels are crossing. So we are creating one channel and a second channel directly close to each other, but they have very, very clearly nearly the same signal. But this was also for us a very important check to see, do we measure really the same signal and the same effect? And interestingly, even the artifacts are doubled within this within these designs. Yeah. So if I look here in different channels, you can see this artifact is there. And here the full data plot might give us even a nicer indicator, right? So you can nicely see here that this event was present throughout most of the channels. Yeah, so you can assume that this is mainly an artifact that occurred in all of the channels. So in such a case, if your motion artifact algorithm is not able to detect this or move that, you can also decide on manual intervention. So basically saying, okay, there were artifacts that my preprocessing didn't work for. So you basically select these regions yourself. And so, for example, this part here, and then you could potentially also say, okay, I want to remove this artifact from my data set directly. This is really manual interference, so it's not advised to do that. But in case this is the only way how you can basically recover your data, since you tried different preprocessing parameters, then this would be one option where you can have the same step applied for all the measures. Yeah. Then, of course, it's the question what you induce with this afterwards. But if you look at the preprocessing afterwards, it might not have a huge influence on the data, but it can have, of course, right? So you have to be careful with this. But there are certain moments in time where your data set is, where you are at this edge. Most importantly, that you report in detail what happened, and also make clear that this event is really something that everybody can replicate. Yeah. So how do you replicate that this event happened? So what is usually done, if you look into the data set, you see that here was a manual interpolation of all channels performed, and then you see the data points where the monotonic interpolation was performed on all channels with the specific moments in time where it was applied. So you can really see where it's happening, but this is really the last resort, only if you can't recover your channel in another manner. Okay, now one interesting aspect here, when we look at our distribution of the data before performing any preprocessing, we can just run a correlation of our signal with the with every other channel within your within our design. And you can see, of course, since we have this heartbeat component, luckily in all our signals, you can see that this is highly correlated throughout the map. And this is a nice, easy way to basically also get one measure for your whole design, because you can do this correlation matrix. You can also just automatically compute and get one standard value for all your pre-processing parameters to get an idea, okay, is this true for all my subsets? So if I redo this after the pre-processing, I didn't include short channels right now. I just rerun the seed-based correlation on this channel. You can still see that there's a high correlation within the map, right? So it was not only the heartbeat component. There seems to be something more that gives us a high correlation. So let's include the short channels into our correction. So just applying the short channels here. And then run the same thing again. And now you can see we have a very focal correlation with the other channels, which are more also in the region where we want to look at them. So this is also like signal quality in the sense of completely data driven in this case. So I didn't load any paradigm. Can of course just to make it a bit easier to look at it, I just load the data to it. So here you can see now that that we now have a clear, nice hemodynamic response that we generated based on the rejection of, or the short channel correction. And this is also part of the signal quality, because beforehand we had a high correlation across all the channels, which was not driven by the hemodynamic signals that we are interested in. So it's really important that even our signal looked very nice, it looked really great. We have to take care that this is not driven by a general factor. And that's one of the examples where you can nicely see also now a difference between left and right hemisphere to these responses. So you see that for the one condition, so we have a left-right finger tapping condition here. You see that for one, we have a unilateral activity. For the second one, we have a bilateral activity, which was not present before. So this is also something that is nicely seen to recover. And then looking at our cross channel, just to do the full circle. So this is our first channel. This is the second channel. You can see that it really covers the same information. And this you also can see here in the event-related averages. You look at them. Sorry, I'll just put them away like this. Yeah, you can see that even the standard deviation looks very, very similar, which is a nice result. Okay, to wrap things up, I want to show you one data set which has a bit more information across the whole head. So this data set is was acquired quite recently, and it basically covers really the like the whole head, as you can see here. So it has a lot of channels that you can see, but this also gives us a lot of challenges, because now if you look at the amount of channels, these are all the channels that you would have to make green in your, or to basically optimize in your signal processing. So if you really want to do that individually, that will take too much time. You're not able to do each and individual. So you really have to do a first very good setup and then try to optimize specific regions. So let's look at the channel quality again. And now you can see that the channels that are removed are here grayed out. So we don't have the signal in here. But we can visualize the map on top. That is maybe easier to look at it. So just remove the clear channel mask. Yeah, there you can see that we have clearly a difference here. These channels are all rejected. Yeah. So let's look into one of these channels, and you can clearly see they are not as good, right? So this is what, for example, one of the channels where you could think, okay, this is clearly having like, it looks more like a deoxy channel, so to say. So let's look at this with the the other preprocessing. So I'm opening the data set again, and I run the CV. So, and I do preprocessing, and I just run the CV now. And go. Just checking if the value is in the CV here. And I overlay only one wavelength. So now you can see that if I look at the CV rejection, there was no channel rejected. So the CV was more a fan of, okay, this signal has still a high variation in there. I can still see some of the components. It got like a bit harder for the signal to basically converge. You can see also here that you have this pattern quite clearly, and this also overlaps with the pattern here. So here you have to invert. So what is here gray is on this map it's red. Yeah. So they are locating exactly the same channels, just the cutoff is different. And these are default cutoff values. So that's the challenge that you have to face. You have to decide on your data how you set the threshold and what to do with this threshold. And since it's a threshold decision, looking at this data here, it doesn't look like you would need to remove it. So there the question would be how you interact with such a data. And usually you can be a bit more liberal and say, okay, I reduce my threshold and also include channels that are maybe having a bit lower value for the respective thresholds. So here, for example, these values were still about 0.6, so they are still quite okay. Yeah, so 0.6-ish. But I wouldn't think that after preprocessing I would not be able to recover that. And let's try to just preprocess without the short channels. And we don't need to do the channel correction. So we look at this part here, and you can still see a little tiny bump, but the rest of the signal was nicely recovered from the time course. So even in the channels where can just run a correlation again from this one, you can see that this distribution is quite focal, but that's also the one that still seems to have really included the same signal. So just a take-home message here, just because the channel rejection tells you to not include this channel in your analysis, it's not always the case that this default value that you've used does apply to your data set. It might be that you have to first figure out for your data set which is the optimal cutoff value to really reject a certain channel. So just looking at one more aspect on the motion artifacts. So specific artifacts could happen in specific regions and in specific moments in time. So they might affect only certain channels. So here you can see that they have a more focal part. Yeah, so you can see that here, and this is due to our cap that has so many channels, and like a specific part might not be that it touches too well on the whole system. So these cases could happen, and you can see they are happening left and right, but within there is more or less fine, right? So the motion artifacts are really different across channels. So if you look at the motion artifacts in an article and they're showing your channel time course, this is just half of the story. It also makes it different across channels. So when you do the correction, you have to just make sure that after your correction, that there are no artifacts with respect to motion that are different across the channels. That's just an important factor. And here, if this is the residual motion that was not corrected, that is totally fine. But it's just important that it's basically really gone on both sides. Yeah, and you see that the amplitude difference compared to the hemodynamics that we are looking for is much different. Okay, final thing before I finish, because I think I'm otherwise running out of time. Just one data set which is really interesting on the hemodynamics, so the extracerebral. So here you can see very clearly just a pattern. I just used the trimmed one. It's a bit cleaner on the time course. Yeah, so here you see it a bit better. So you can see that in this data set, which was a bilateral hand movement task, we can't really clearly see a response. And that is one of the things where the extracerebral is really in effect. You can always see this double pattern that is there across all the channels, and you can see it's even in the short channels. So if I compare a normal channel and a short channel, they look so similar. Right? So that is something where, yeah, it's becoming tricky. We won't cover this today, but if you want to use short channels for correction and you have artifacts in your short channel, that's another problem that you have to. It's then better to have more short channels that you can then use to recover your signal. Okay, so we just preprocess again without the short channel correction to see if the signal was driven by these moments. But what you can really clearly see here, short channel signal and the normal signal are very, very similar. Yeah, and that since we are looking for a signal that didn't cover that covered the cortex, this is something where we should yeah, just pay attention to. So running the correction again. So fNIRS data preprocessing and just performing the short channel correction. The filtering doesn't really matter because it's already filtered. You can see now that we really get responses where we are clearly seeing the right event. I can add a bit more data here. You can also see that the shape does not only include the peak, but it also goes down nicely in these events. Yeah. And this wasn't there before doing the correction, but you also weren't directly able to eyeball that this combination of short channel and normal channel would end up in a very focal response. So from here, just doing the check with our GLM very quickly, just to check if this fits our model. You can nicely see that this fits, and it also goes into a specificity on the respective channels. So it also covers the right region. So this is a functional check which you can always perform, even if you don't see the activity before correcting. It is still potentially present in your data after performing this extracerebral removal. Having external sources of signal in addition. For example, if you look at this signal. Yes, so the data plotter, manager, add to data plotter, tools, data plotter, check where there it is. And so if you add additional extra components, like for example, specific accelerometer data, you can also see if there's anything that might relate to the signal with respect to your movement artifacts. And I think maybe you remember the part which we cleaned from the data. You can see here from the movement artifacts that this was really induced by movement. And here in the later part, we basically removed this part from the data, which is also highly linked. So external signals next to the short channels would also be helpful to understand why certain signal quality is there and why we potentially face certain problems with our data quality. Okay, with that, I would like to thank you for your attention, and still open for questions or any discussions.
Thank you so much. That was fantastic, and it was both really interesting and also really helpful, I think. Okay, so let's open the floor to questions. You can either type in the chat and I'll read them, or you can raise your hands as you like.